Hey guys, so today we're going to be discussing the basic concepts of hemoglobin and how oxygen is involved in this process. So just to kind of review what exactly we're going to be going over, we're going to be talking about how oxygen binds to the heme and any of the structural changes that result as a fact. We're going to discuss the binding capacity of oxygen in the lungs versus the capillaries, and then we're going to round it off with how carbon dioxide interacts with water can alter the capillary pH. Alright, so what exactly is heme? Well, if you can see on this design right here, there is a iron atom situated right in the center, surrounded by these four what are called pyrrole rings. Now that combined together is known as a protoporphin, the four pyrrole rings, and then there's going to be a couple side chains. That's going to be the four methyls, the two vinyls, and the two proponate groups that you kind of see within this picture. Alright, so how exactly does oxygen bind to heme? How does it all work? It starts out with that iron that we initially saw in the other picture. It can form two additional bonds, which are known as the fifth and sixth coordination site. The fifth site is actually occupied by a proximal histidine, which you can see in this picture. That's this little doodad right here. But the distal histidine site is actually open for oxygen binding. This is kind of situated to kind of prevent oxidation between the heme and the iron to begin with, but it's also an open spot available for further binding. So as it currently is in its deoxygenated state, the iron doesn't actually fit in the picture because the electrons take up too much space. There's not enough for it to actually be able to situate clearly within the picture. So when the oxygen binds, these electrons are able to shift and cause the iron molecule to kind of situate itself right into the picture. As you can see, this is when you can tell that it's oxygenated and that the oxygen molecule is binding with hemoglobin, because the iron is now caught right in the center of those pyrroles and the porphyrin ring that we had discussed. So at that point in time, that's when the oxygen is stabilized and will form a hydrogen bond with the distal histidine to kind of stabilize everything further. Now, to go into the actual details of what's going on there, you initially start with a drop in the blood pH. Now, this will stimulate numerous signals, which we'll talk about momentarily, and cause this increase in oxygen affinity of the heme. Now, the heme is going to start picking up more oxygen molecules and start binding with them, like we just talked about with the iron kind of reducing size and snugging in. That's all due to these oxygen being picked up. And now this binding with the distal histidine has a further structural relevance in that when the oxygen binds with that distal histidine, it actually causes changes in the proximal histidine in the alpha helix, which is all situated together. This all causes a major shift to occur and eventually dictates the quaternary structure actually rotating approximately 15 degrees and transitioning from a tense state to a relaxed state. And this is what causes that oxygen to be bound so tightly and in place, because once that rotation occurs, it's completely snug as a bug, for lack of a better word. Now, back to this oxygen binding capacity. What exactly is going on with that, and where is it at relatively from the lungs versus the capillaries? So, like I said previously, it's these increased carbon dioxide levels which are stimulating the hemoglobin response to begin with. The increased CO2 lowers the overall blood pH, and this causes the oxygen affinity of the hemoglobin to decrease. This means that hemoglobin isn't going to be bonded so strongly with those oxygen molecules is going to start releasing them. Now, that's going to stimulate this greater release of oxygen when there is pH change. Now, you can still have oxygen be released even when the pH doesn't change, but not as much molecules are going to be released. And now all of this is due to an allosteric regulator known as 2,3-BPG. There's a longer terminology for it, but I couldn't exactly pronounce it properly, so I figured we would keep it with the abbreviated sense. So what exactly is going on is this 2,3-BPG binds to the hemoglobin and is what is causing this hemoglobin's oxygen affinity to reduce. So because the 2,3-BPG has such a preference for deoxygenated hemoglobin, it's all actually it's stabilizing it by reducing that oxygen affinity and causing it to drop off those molecules and becoming this deoxygenated hemoglobin in which it prefers. So the main point behind all of this is that, back to our original question of lungs versus capillaries, is that the binding capacity is actually much stronger in the lungs, because when you think about it, hemoglobin is in the lungs to grab this oxygen. We breathe in these oxygen molecules, and the heme is able to take it from our lungs to the capillaries, where we're able to transition it into tissues and so forth throughout the rest of our body. So binding capacity has to be significantly stronger in the lungs, where this oxygen affinity is high, causing the hemoglobin to grab these molecules and hold on to them tightly. Now, as soon as we get to the capillaries, where we want these hemoglobin molecules to release the oxygen so that we can circulate it through our system, that's when the 2,3-BPG comes in and is going to allow that reduction of oxygen affinity to deoxygenate it and reduce that binding capacity like we were talking about. So our final question for today is, how does the carbon dioxide interacting with water play a role in specifically the capillary pH? It's actually a really simple concept, kind of based off of what we were just talking about. So when carbon dioxide interacts with water, it produces what's known as carbonic acid, and this acidity is going to not only increase the carbon dioxide levels in the blood, but decrease pH levels overall. And like we previously talked about, decreased pH stimulates this response with 2,3-BPG and with hemoglobin, and stimulates hemoglobin to have that greater oxygen affinity, hold on to those oxygen molecules more stringently, and essentially the whole process is repeated. So the hemoglobin is going to pick up more oxygen molecules, and 2,3-BPG is going to say when it should essentially drop the molecules, and the whole process just repeats itself. So thank you for listening to my presentation. I hope you enjoyed my graphics, and good luck this week, guys.